6.6 The effect of changing conditions on equilibria. As you have seen, Le Chatelier's principle states that when a system at equilibrium is disturbed, the equilibrium position moves in the direction that will reduce the disturbance. You can use Le Chatelier's principle to predict the qualitative effect of changing temperature and concentration on the position of equilibrium. In this topic, you look at what underlies this by examining the effect of changing conditions on the equilibrium constant Kc. Changing the temperature changes the value of the equilibrium constant Kc. Whether Kc increases or decreases depends on whether the reaction is exothermic or endothermic. If equilibrium constant Kc increases in value, the equilibrium moves to the right, that is, the forward reaction, more product. If it decreases in value, the equilibrium moves to the left, that is, the backward reaction, less product. This is because the expression for Kc is always of the form products divided by reactants. The general rule is that for an exothermic reaction, delta H is negative, increasing the temperature decreases the equilibrium constant. For an endothermic reaction, delta H is positive, increasing the temperature increases the equilibrium constant. So for an exothermic reaction, increasing the temperature will move the equilibrium to the left. For an endothermic reaction, increasing the temperature will move the equilibrium to the right. First, remember that the equilibrium constant does not change unless the temperature changes. Look at the following example. C2H5OH plus CH3CO2H is equal to and can be converted back from CH3CO2C2H5 plus H2O. Le Chatelier's principle tells you that the equilibrium will react to any disturbance by moving in such a way as to reduce the disturbance. Imagine you add more ethanol, thereby increasing its concentration. The only way this concentration can be reduced is by some of the ethanol reacting with ethanoic acid, producing more ethyl ethanoate and water. Eventually, a new equilibrium will be set up with relatively more of the products. The equilibrium has moved to the right, or in the forward direction. Let us see how this works mathematically. You know that Kc is equal to CH3CO2C2H5 times H2O, the whole thing divided by CH3CO2H times C2H5OH. Remember that Kc remains constant provided that temperature remains constant as well. Adding ethanol makes the bottom line of the equilibrium law expression larger. To restore the situation, some of the ethanol reacts with ethanoic acid, reducing both the concentration in the bottom line of the fraction. This produces more ethyl ethanoate and water, thus increasing the value in the top line of the fraction. The combined effect is to restore the fraction to the original value of Kc. The size of the equilibrium constant Kc can tell us about the composition of the equilibrium mixture. The equilibrium expression is always of the general form, products divided by reactants. So, if Kc is much greater than 1, products predominate over reactants and the equilibrium position is over to the right. If Kc is much less than 1, reactants predominate and the equilibrium position is over to the left. Reactions where the equilibrium constant is greater than 10 to the power of 10 are usually regarded as going to completion, whilst those with an equilibrium constant of less than 10 to the power of minus 10 are regarded as not taking place at all. Catalysts have no effect whatsoever on the value of Kc and therefore the position of equilibrium. This is because they affect the rate of both forward and back reaction equally. They do this by reducing the activation energy for the reactants. They do, however, affect the rate at which equilibrium is attained. This is important in industrial processes. Reversible reactions may take place in the gas phase as well as in solution. These include many reactions of industrial importance, such as the manufacture of ammonia by the Haber process and key stage of the contact process for making sulfuric acid. Gaseous equilibria also obey the equilibrium law, but usually their concentrations are expressed in a different way, using partial pressures rather than concentrations.